So I want to pick up discussing now that we've set the stage of our wavelength, our frequency, and this idea of color, we can sort of expand our conversation and understand that the visible wavelengths of light that we can view, again, which falls somewhere between about 400, 550, up to about 700, 750 nanometers of light, where at the low end of the wavelengths we have our violet light, and at the high ends we have our red lights. Right? This represents only a very small section of the entire, what we would call the electromagnetic spectrum, or all of the waves that can move or that exist moving at the speed of light. And if we think about it, right, this is just a little sliver of wavelengths, right? We can have wavelengths that are both longer and shorter than visible light, and they're going to exist, right? They're there, but we cannot observe them, right? Our eyes can't observe those wavelengths. So we're going to spend the next couple minutes just sort of looking briefly at the major types of electromagnetic waves beyond the visible. So if we first look for lower wavelengths, right? So these are shorter wavelength types of light. If we go just beyond the violet, just a little shorter than the violet, we get to what we call ultraviolet, right? And we all are familiar with ultraviolet light because of the idea that it comes from the sun, right? And that we wear things like sunscreen to protect our skin from these ultraviolet rays, right? And so that's ultraviolet light. If we go even shorter, we get to a type of waves that are called X-rays. And again, I think we're all familiar with the major use of this type of these wavelengths of light in using them to take X-rays to image the bones and certain organs of the body. And if we move to even shorter wavelengths, we get to what are known as gamma rays. And these are wavelengths with the shortest wavelengths. Now, understanding that as we're shortening the wavelength, we are increasing the frequency. So the frequency is going from around 10 to the 14, 10 to the 14, 15, all the way out to 10 to the 20th. Right? So as those wavelengths get shorter, those frequencies are getting higher. Now, something we'll get into a little more detail later is that also means that the energy is getting higher. So we'll see later on that as the wavelength gets smaller and the frequency gets higher, the energy of those waves gets higher. And so one common factor that these types of waves, these ultraviolet, these X-rays, these gamma rays, is that they're higher energy than visible. And they're high enough that they can damage biological tissue, right? So ultraviolet can burn the skin, right? X-rays, if used, inappropriately, can damage internal organs, right? Can cause damage in the body, right? That's why when we get X-rays, we sometimes wear a lead vest, or the people administering them stand behind lead doors, right? Because they can be harmful to tissues. And gamma rays, right? They can cause severe damage to bodily tissues and ultimately lead to death, right? If overexposed. Now, gamma rays, not all bad, of course. Gamma rays are what we use to treat cancer when we think about radiation therapy, right? And the whole purpose there is to kill the cells that we don't want, right? So we try to selectively target the cancer cells to kill them using these gamma rays, trying to minimize the effects on the healthy tissue. But of course, that's not always possible, and we get side effects, right? Okay, so let's turn our attention to the other side of the spectrum. So we're going to go now to longer wavelengths or lower frequencies of electromagnetic rays. So if we go beyond the red and we get to higher wavelengths, we get to what's called infrared. Okay? Now, infrared light is most famously known as thermal energy, right? So when we think about thermal energy, that's infrared light, right? And so if we think about thermal imaging or infrared imaging, right, this is what we think about, right? And all creatures, all living creatures give off infrared radiation, right? Give off waves in these wavelengths. This is also what's commonly used in things like remote controls. Now, if we go to even longer wavelengths, we get into a regime known as microwaves, which we commonly know as a way to cook, right? So microwaves are what's used in microwave ovens to heat up and to cook food, and it does this by exciting or activating water molecules, and it heats up those water molecules as they start to move faster and faster due to the microwaves, and that heats up the food. Now, microwaves are also used for communication and so forth. And we get even to longer wavelengths. We get into sort of these large section of very high wavelength electromagnetic waves that are what's known as radio waves. And this is where we see the bulk of the communication techniques, right? Things like TV signals, radio signals, satellite signals, right? All exist, cellular phone signals, all exist up in this radio wave part of the spectrum, where we have, again, very long wavelengths, relatively low frequencies, and, as we might think, low energies, right? So infrared, microwaves, radio waves, these are forms of electromagnetic waves that are non-harmful, right? Just like visible. Right? So we can be exposed to these and not really cause any kind of biological damage. So, quick overview of the spectrum and a couple key things to keep in mind, right? We've already talked about the inverse relationship between frequency and wavelength. So as we say decrease the wavelength, we increase the frequency and vice versa. And if we think about, we can add in the idea of energy here, that as I decrease the wavelength, I increase the energy. And so we get that same inverse relationship between wavelength and energy. Now, what that also means is that frequency and wavelength and energy are directly related. So as frequency goes up, just like we said here, moving to the right, energy also goes up. So we have these different relationships between wavelength, frequency, and energy.